So you have the pleasure now to have Vladimir.
Just a question.
Yes.
Will we go immediately after the talk, or more or less?
We can vote. It's just that, yeah, because otherwise it's like an
That's right. No, I would be in favor of doing that.
Yeah, because then we can be a little earlier than usual,
the others?
Because this restaurant gets full around 7.
Can you say again the name of the restaurant?
Versailles. There's the like French, but Spanish version. Versailles.
You'll notice it is just as elegant.
The Little Havana, Calle 8 in the 8th Street. So we have the pleasure now having Vladimir, as I was saying. So looking at his CV, I worked on it yesterday. I'm impressed that he has so many titles. So he is an electrical engineer from the Universidad San Francisco de Quito, but also physicist from the Universidad San Francisco de Quito. But then he did 2 masters, one in electrical engineering and another one in physics in Urbana-Champaign, and a PhD in physics in Urbana. Is that correct?
Yeah.
So 5 titles. It would be in German, it would be doctor, diploma.
You don't have to say about my past life.
He's now at Emory University, and he tells about Spatial Localizers for electrons and insulators. Thank you very much.
Thank you, Bernardo. Thank you, by the way, Bernardo, Rafael, for organizing this and for inviting me. I think it's a great initiative to have physicists and mathematicians together, and it's been very productive for me, at least. I'm sure for others too. I'm looking forward to further discussions. So today I'm going to talk about local state representations of bands in insulators. So this is a work that has been done in collaboration with Alex, and with the heavy lifting of this was carried by Helen, my grad student. And also we had the participation of Ethan Wang, who was my undergrad student. Now he's a doctoral student at in Urbana-Champaign. Okay, so the question is very simple. Where are the electrons in an insulator? This question is relevant because the role of Wannier centers. Wannier centers are the centers of charge. We can think of them as the centers of charge in an insulator. Their flow, the relative position, and even whether they are well-defined or not is central to band topology. And in particular, we have in mind the intersection between topology and correlations. And so we believe that having a local basis for influence with local interactions is the right starting point to have an understanding of this complicated correlated process. Okay, so I know that we have here a mixture of physicists and mathematicians, so I want to spend some time to make sure that we're all on the same page. So I will just introduce the notion of Wannier centers and how they come about and why they are important. And so the sort of like canonical toy model that one has, or which is also the simplest model, is to consider this so-called Sucre model that can be a toy model for polyacetylene, where you have a unit cell that has 2 sides, A and B, and you have a dimerization of the Hawkins. And so I'm going to set this intercell Hawking as 1, and this other one, the intracell Hawking as 1, and the intercell Hawking as gamma. And so if we look at the 2 insulating phases that we can have when we dimerize these Hawkings, we see that they are, of course, separated by a transition point. And so the question is, what's the difference between these 2 insulating phases, the one on the left and the one on the right? And the answer is that these 2 phases differ by the dipole moment, the electric dipole moment. By the way, please feel free to interrupt at that moment. And so how do we know that they have different dipole moments? Well, one thing we can do is open the boundaries in this system. When we do that, we see that in the phase where the intercell Hawking is shorter than the intercell Hawking, we have these edge modes. And if we fill this system up to half filling inside this gray square, this the insulating phase that has dipole moment 1/2, or that we claim that has dipole moment 1/2, what we see is that we have some charge density on the boundaries. Whereas if we do the same thing on this wide region of the sort of the phase diagram, we don't see these edge modes. And accordingly, if we fill up to Fermi level at 0 energy, we will have some uniform distribution of charge. So this is very reminiscent of what happens in continuous dielectrics, right? Where there's some boundary charge that's given by the polarization. So this is sort of like the notion of bulk quantity, the bulk polarization, dictating what happens at the boundary of the system. And so it's what we see essentially is that the lattices also exhibit this realization, and I think this is the core principle of the bulk boundary correspondence in topological insulators. The fact that we have this correspondence with continuous dielectrics. Okay, and so how can we explain this difference in polarization? So there's this very simple picture as a classical picture of point charges. The statement is that if you have, in the trivial phase, say you have the unit cell here with some ion, the white circle, and then the electrons are going to be these blue dots. And so the cartoon picture of what's going on is that in the trivial phase, you have electrons sitting on top of the ions first. So you could see that it's an inert from the point of view boundary charge. But in this other phase, you have the electrons sitting in between the ions. And as long as you have inversion symmetry, these are the only two possible configurations. So this tells us right away that in the practice of inversion symmetry, we have these two so-called symmetry protected topological phases. With break inversion symmetry, we can continuously deform one into the other. And so notice here that if we enforce inversion symmetry, we can have two sort of configurations. We can have either 3 electrons or 5 electrons, but we cannot afford to have 4 electrons while respecting inversion symmetry if we open the boundaries. Okay? And so this is the origin of the sort of fractional charge that we get at the boundaries, because now in this non-trivial configuration, we can define this filling anomaly, which is the ionic charge minus the number of electrons, modulo 2. In this case, under inversion symmetry, we have something modulo 2. More generally, we would do this modulo symmetry related sectors. So if it's protected by C4, for example, then we would modulo 4, etc. And so in this case, the filling anomaly is 1 mod 2. And by symmetry, whatever this excess of charge we have in the system has to be equally distributed across the two halves, which means that each half of the system must carry a fractional charge P over 2. And by the way, just want to clarify this: a non-interacting system, these fractional charges are just density of states. Okay, so in addition to dipole moments, some time ago we were wondering, okay, if we follow the same principle, can we generate also higher multiple moments, quadruple moments, octuple moments that are also characterized by not only some corner features, but also edge features like lower dimensional topological states on the boundaries. So for example, in the case of the quadruple, we not only have fractional charges at the corners, but also edge polarizations. And in the case of the octuple, we will have surface quadruples, hinge polarizations, and corner charges. And sort of like in order to see how corner charges can come about using the same sort of like toy picture of what's going on with the distribution of charges here, we can envision a configuration like I put there, where each unit cell has 3 electrons. And so under periodic boundary conditions, you can see that this preserves C4 symmetry. The reason I'm putting 3 is that whatever dipole moment this induces is compensated by the dipole moment of these other 2 electrons. So the overall dipole moment is 0. But the question is, can we have something with vanishing dipole moment, but higher moments, right? And so if you put this, if you tile this up with formalities, now you open the boundaries. You know that your Hamiltonian will have to preserve the symmetry. In this case, C4 symmetry. But if you just do that exercise here, you see that the boundary is not respecting the symmetry. Of course, that's not a feasible configuration for the Hamiltonian. What the Hamiltonian will do is enforce the symmetry. And so we can try to play the game of deforming what's happening on the boundary to try to restore C4 symmetry. And so I'm displacing these charges down and these to the right, as shown here. But now you see that we've almost restored C4 symmetry, except that we lack an electron there. And that's the origin of a new filling anomaly. This filling anomaly is induced by the presence of corners, right? If we have periodic boundary conditions along one direction, so that we have some open edge, we won't have a filling anomaly. This exists on the presence of corners. So one way to fix that is to remove the 3 electrons on these 3 corners. That's a filling anomaly of 3, because I've now restored symmetry, but at the cost of charge neutrality. But I can also do another thing. I can also add an electron, right? In each of these 2 configurations, the filling anomaly is well-defined modulo 4, right? And so this is you can play with toy type binding models to realize this configuration in the bulk. And sure enough, if you do that under open boundary conditions, you see fractional correlation. Okay, and so given that you can have these dipole moments or quadrupole moments in 1 or 2D systems, or even multiple moments in 3D. Now, by the arguments of Tile span or Laughlin arguments, one can generate Wannier flow associated with these moments. And so there's a hierarchy of topological phases that relate, say, the dipole moment to a Chern insulator via charge pump. And if you do a spin-full version of this, you can have a quantum spin hole, and then you can also generate, what are now known as higher order topological insulators that build upon this notion of a system with corner charges, by the same procedure of charge pumping, topological charge pumping, into generating something that has chiral hinge states or also helical hinge states. And so this is all to say that looking at where the electrons sit in a material are central to topological boundary. And so now I'm going to go back to sort of like review how we solve the problem in 1D of finding these Wannier centers, these centers of electric charge. And that will sort of like serve as a way to generalize the problem to 2D. Okay, so we want to essentially go from a block basis to a local basis. If we have access to the entire Hilbert space, we can always have very, very localized spaces, right? So we can go from a sort of like extended basis for the system to something that's very local. Now we have the restriction that we're only filling states below the Fermi energy, and therefore this perfect localization is not going to be possible. And so the best we can do is to generate the so-called maximally localized Wannier functions. And this is work that started back in 1937 by Wannier, but it took some more than 50 years to recognize the utility of this.
Okay, that's a good question. Is it proven that they're their maximum of some localization metric, or is it just a name? Because when I see maximally localized, I expect to then find here are all the ways you can localize, and the maximum is achieved here. Is that done?
Yes. Yes, that's done. These are maximally localized.
Okay.
And so, but you touch on a crucial point, which is that these sort of like block states, they have some gauge freedom, right? And so there's there's many ways in which I can combine these. And the question is, how do I maximally localize this?
There's also some functional that you know that is minimized now in that side.
Exactly. So if you go to packages like Wannier, for example, what they do is they have this localization, a measure of the spread of the function, and they do iterations to minimize that spread. Yeah. And so the basic idea is you have some occupied band, and you do a linear superposition of these guys. That will give you something that is the closest that you can get to the local basis. Right. And crucially, the centers of mass of these functions are the so-called Wannier centers, which are essentially the dots that I was playing with earlier. And even though these things here there's some gauge freedom, when they are maximally localized, the center of these maximally localized functions are gauge variant. And yeah, this is just a statement that I guess there was ahead of this slide, but this is just to say that there's some gauge freedom, so it's not obvious which combination of one has to choose these sort of like phases in front of these states to maximally localize these functions. Okay, but if we know that the Wannier centers are gauge invariant, then we can just have a gauge invariant formulation of the problem to not have to deal with minimizing these use. And it turns out that these Wannier centers are given by a very phase calculation over the brilliance of the system. And so you have your partition of your Hilbert space given by the two bands. You choose this lower band, and you use these states to define some very connection as a function of K, the crystal moment. And when you do the holonomy of this thing, will give you the collection of Wannier centers. If you have just one band, you will have just one Wannier center, which is essentially the very this calculation. So this quantity mu here measures the displacement of the electrons relative to the center of a unit cell. And so this directly gives you access to the dipole moment, the displacement of the electron relative to the.
Sorry, there is mod 2 or mod 1 because I don't understand that equation.
Mod 1. Sorry, I'm setting the unit cell to 1.
Okay.
And so if you get a very phase of 0, means the electrons are aligned with are on top of the ions, right? And as this very phase is away from 0, the displacement increases. Is defined modulo 1 because if this very phase is 2 pi, the phase is only defined 2 pi, then that means that you're just reassigning your Wannier center to the next unit. Okay. Okay, and so I want to generalize this problem to possibly even non-periodic systems. And so one way to deal with this is there's this beautiful formulation of the problem by Resta in 1998, where he essentially compactifies the position operator into the unit circle of the complex plane by this map here. So this is the usual position operator who exponentiates it, and this is what I'm going to call the Resta position operator. And so essentially, is a way to make an operator for position that's compatible with periodic boundary conditions. Okay, so once we have this Resta operator, what we can do is just solve the eigenvalue problem of diagonalizing the Resta position operator, given that I'm constrained to my Hilbert space of occupied bands. Right, so this is sort of like a projector, half projector into the space of occupied bands. And so if I diagonalize this, I will have these spaces here that will encode the Wannier centers, that's the xj, and the corresponding Wannier functions as the eigenstates of those values.
The psi i's are the eigenstates, or
these are the energy states.
it's the energy eigenstates.
Yes, and I'm constraining them to go from 1 all the way to the occupied number of states. yeah, I'm not labeling this by K anymore because I'm possibly considering disorder. But the assumption is I have some gap and I'm taking anything below a gap.
So is there a missing psi in the second half of that?
Actually, yeah. Not. It's not. That's why I called it the half projector. So I'm just redefining a canonical basis, and this is just to avoid, having a bunch of zeros in my tool.
I would say it's like a partial isometry, I guess, that you have.
Yeah.
No?
Yeah.
But somehow it looks strange, the formula, indeed, because xj on the right. No, it's the xj is in the basis I. Yeah. You just have the.
Yeah. So if you think a matrix, right, the entries are now the occupied states. If I do the full projector, I'll essentially something similar, but I'll have a bunch of zeros in the null space of the projector.
This is just the same thing we do with the bot index, to just take the rectangle and stuff.
Yeah, exactly. Okay. Just making our lives easier. Do not have to deal with a bunch. Okay. So now I'm going to motivate a localizer using this construction, the rest construction. So what I'm going to do is I'm going to move this term to the left. So it's just recasting the eigenvalue problem like that. And now I'm going to, more generally, consider what I call the rest localizer, where I essentially, which is this operator here in parentheses. Right? And I'm going to find this localizer indicator function. I think Terry calls it pseudospectrum, or is related to pseudospectrum. And so notice that the crucial statement is that when this object here hits 0, then at that position, I have a Wannier, right? Because when this is 0, I've recovered the eigenvalue problem. Okay, so sorry, maybe I should clarify something. So here, these are the Wannier centers labeled by J. These are the eigenstates. But here in the rest localizer, I just have a free parameter x. So that's going to, right? I'm exchanging the Wannier centers by some parameter that I'm going to scan. That's a parameter of my mathematical type. And so as I scan this, eventually I will hit these eigenvalues, and the indicator function will hit 0. Okay. Okay, and so that was my first step. The second step that I'm going to use to motivate extensions to 2D is to have a different embedding. So Resta compactified it into the unit circle in the complex plane. We're going to just embed these coordinates of this position operator into the equatorial plane of the blocks. And so, among other things, what that does is, the new, what we call the 1D spatial localizer, is just 2 copies of the Resta localizer. It has now chiral symmetry, which means the spectrum will be symmetric about 0. And but most importantly, now we have a bigger manifold on which we can embed things in higher dimensions. Okay, so before I jump into higher dimensions, I just wanted to work out a simple example. So here we have, again, the SSH model that I introduced at the very beginning of the talk. But now I've put something that breaks periodicity. I put a domain wall here. I have a topological state. This system has chiral symmetry, so the state with fractional charge also, it's a 0 energy eigenstate. And so under periodic boundary conditions, so in the absence of this guy, what I would have is something that's fully gapped. So that's my gap, and I'm going to assume I'm filling all the blue bands. Okay. Now, if I calculate the spectrum for this system here with the defect, what I'll see is that I have these 2 red dots. To have this with periodic boundary conditions, I'll need to put another such domain wall, right? And lives here, the other guy will live somewhere else. And so if I now do my projection into the blue bands, and I calculate the super spectrum of this, or the the full spectrum, I'm not plotting everything, just the vicinity around 0. What I find is something like that. So in the gray lines delineate the unit cells, and what we see here is that the Wannier centers are in the middle of the unit cell on the left. So that's illustrated by these dots. But then they switch into being between unit cells. And sure enough, if I instead project into the red states, I have my topological state advantage. Okay. And so again, so here we clearly see that we have some state that's associated with a change in polarization. Here I have polarization 0, whereas here I have polarization 1/2. And so this is the simplest example of something that has broken translation symmetry, but we can see that this sort of like localizer formulation can capture that. Okay. So now I'm going to talk about the 2D spatial localizer, and I'm going to first discuss eigenvalues, which map to the Wannier centers or generalizations of Wannier centers, and then I'll discuss the spatial localizer eigenstates, which will give us the Wannier functions. Okay, so in constructing these localizers, it's important to preserve the non-commutative geometry of the product. Right? This is something that we don't have in 1D, but in 2D, these things don't necessarily commute X and Y. Once you project them, you have this non-commutative geometry. In Landau levels, for example, that's given by the magnetic translation group, and then in crystalline insulators, more generally, you have the very connection. Right? And so, in particular, there are some extreme cases, topological insulators. It's said that you cannot have a Wannier description that's made of Wannier functions that are exponentially localized. So the usual way to think about Chern insulators or quantum spin insulators in our community is to do some partial localization. In other words, we keep some block-like states along one direction, and then we localize them. We do a very phase calculation along the orthogonal direction. And so at each ky slice, for example, we have some Wannier center along X. And when you have Chern insulator, what you have is a winding of the Wannier center along ky. So this is essentially the Taule's bond, or the Locking argument is related to this spectral flow of the Wannier centers. If you have a quantum spin insulator, you have something like that, where this point here is protected by Kramer's degeneracy. And so this is how we capture things, like partial localization. But in our problem, we want to go further and say, can we actually localize Wannier functions, or have more generally local state descriptions of these systems? And so I don't know how to best introduce the localizer other than to say this is what we have. And so, so essentially, the spirit is that earlier we used the Pauli matrices to accommodate periodic boundary conditions along one direction. Now we have two directions, so we need a larger clip project. So what we use is the Dirac matrices, gamma 1 to 4, where these anti-commute. And then these functions here, this is goes as the cosine of x, the other one goes the sine of x, and this xi here are just to move the tip of the locus.
So for the Dirac matrices, one of them squares to -1, the other one squared to 1. Do you want them all squaring to 1?
I remember having this discussion with my grad student.
We had it.
We had
on Zoom.
Do you remember this?
The answer is you're not using Dirac matrices.
Yeah.
You're using the square of the identity.
Yeah.
So Halen and I worked this out.
Yeah. The Dirac matrices have a specific 100-year-old definition, and you're not using those.
I see. So this notation is incorrect.
Just Clifford. Yeah, Clifford. We'll work on the terminology.
It's right.
Okay.
It's right in the manuscript.
Okay. As a physicist, we don't differentiate that. Yeah, and of course, two of the three authors of this paper have also worked out embeddings into to accommodate periodic bundle.
But we didn't have the E occupied there.
Yeah, so yeah,
So it's
but the notion of
variation of that. I think the functions in space were the same, but right. I mean, we had one that was there.
yeah, it's a different local. You were dealing with the spectral, right? Yeah. So it's a different construction, but still we call it localizer because it follows the same principle. Yeah. I think you're embedding this on a sphere. Actually, we're embedding this on a torus.
No. We also had open source, but you have this E occupied there, while in our case it's not there. It's
right.
The positions, and then there was one gamma matrix more, which had the Hamiltonian. So what you put there now as a partial isometry. Anyway.
Okay. So yeah, maybe just one more comment. So essentially, we are embedding. This embedding is on a torus of this the vectorial plane of this higher dimensional sphere, which is the torus. Okay, so now I'm going to discuss some applications of this. What I have here is tungsten diselenide. This is a TMD material. It's it's just 3 atoms thick, but it extends into E, and it's a very appealing material nowadays because you can put stacks of these and have all sorts of topological properties. You can twist them. You can pretty much like the Legos, like playing with them. And so this is the atomic composition of this. Is looking from above is like it has a honeycomb lattice, and there's an effective Hamiltonian that by which you can write the bands closer to the Fermi level have this tungsten character where the couplings between the tungsten is mediated by the selenide atoms. So what I'm putting here as white dots are just the positions of the tungsten. Okay, and this is an effective model for tungsten. And so you can see here the scanning of X and Y.
Why is it selenium 2? Because I see as many black as yellow dots there.
No, there's 2 sitting on top of it. Like here's a view of the side view.
Okay.
So there's 2 of these, one dot.
Yeah. So it's affecting model. There is not the full material Taiwanese model.
Yeah, it's an effective model. And I think this model has like 10 bands. And we're looking at close to 0, close to 10 million.
But you solve the equation in the unit cell, yeah. You calculate everything in a unit cell of this.
Yeah, for under periodic bundle. Okay, so for this guy, we have the Hamiltonian, we project into the bands of interest, and we scan X and Y for the localizer we constructed, and we have here I'm plotting the indicator function, subspectrum, mu of R. And what we see is that indeed, for the most part, it's black, away from 0, but at some places it hits 0. These are these dots. And so this would be the Wannier. And this is an example of something that we go by the name by an obstructed atomic split. It's like the inversion symmetric protected phase in the SSH model that I introduced earlier, where the electrons are really displaced from where the atoms are. So this is a counterintuitive arrangement, right? Where the center of charge, it's not coincident with any of the atoms. And if we look at the localizer eigenstates, I'll go deeper into that later on. We can plot that state here, and sure enough, you see that they are made out of orbitals, atomic orbitals in the tungsten, but the interference pattern is such that the center is here where there's none.
Question: can you do the same thing as in 1D? Like if you move in X and Y, the localizer, the new way to compute them.
That's what. So this is the scanning of X and Y.
The Chern number? Yeah.
Yes. Exactly. So what we would have now is some pattern of Wannier. We're actually my grad student is running these calculations right now. So we have a pattern of Wannier centers, and we can do some topological pump along the third direction, and you'll see that they go different ways.
And how do you do pumping? And
So that depends on the model, but typically what you need to do is you need to add a term that breaks the symmetry that protects the topological phase. And also typically that, you want to preserve the gap. So if your system is chiral symmetric, you need a term that breaks chiral symmetry. And that will introduce some generalizations of Table's pump in the third direction. Happy to talk more about that. Okay, and so here we have sort of like a comparison with the numeric techniques that are out there. In particular, we're comparing the functions spread, so the spread of this function. Our claim is that we want something maximally localized. Okay? And so what we have here is the function spread in red for our result. And in gray and blue, what we get if we run Wannier like the standard software packages that try to find these iterations and as we talked earlier, minimize the spread of this function. And so typically what you do is you give an ansatz to the problem, and then based on that ansatz, the thing runs this optimization algorithm and converges to some value. But what I want to illustrate here is that Wannier crucially depends on the ansatz you give. If I give these ansatz, if I say, okay, start find me maximal localized centers with an ansatz given here, it will still converge to this position, which is the wrong solution. If you only put an ansatz that's located where it should be, then it finds the maximal localized cell.
But it doesn't find all of them.
So this is the iteration, right? This iteration. And this is just one unit cell. And I'm putting here where I put my ansatz. And so if I put my ansatz in the wrong place, we know that the Wannier centers are at the corners of the unit cell.
Oh, so the answer is to the right, I bet you. So this is the total Wannier spread.
This is the total Wannier spread, yeah.
Okay, so it's the Wannier spread of each, you take the spread of each center, and then you take like the root mean square, you take the L2 sum of all of them.
Yes. No, periodic boundary conditions, so you have just one unit cell. And so you have one Wannier function.
Oh, you're really looking for one periodicity.
Yeah, just for one. You're asking periodicity, right? So whatever you find for one unit cell should replicate everything else.
Not used to periodic systems. Strange.
Yeah.
the iteration is what's the iteration parameter? How do you rule your iterations?
Well, there is this package that does the thing. So there is the.
Can you claim that you do one for the spatial localizer as well?
Oh no, this is just as reference. There's no iteration.
Okay.
Sorry. Okay, I see. Yeah.
Which is faster?
Which one is
Faster.
Good question. I've never dealt with this. That's what I have a grad student for. But
I was asking a graduate student, which is faster.
Yeah. I will. But our point was never, I know that one of the appealing things about the localizer is how sparse and how fast it can be.
Yeah.
Here we're projecting things, so we don't.
Yeah, I take money from the computational math program at SF sometimes, so I like the answer.
I will ask. Rafael is very acquainted with Wannier, so I don't know if you.
So yeah.
I'm just wondering. I think Wannier is pretty slow. It's a miserable algorithm.
Yeah, it's all one is
So what because I know the underlying algorithm is used in other areas. It's very slow. Scales fast.
Yeah.
So I just.
Yeah, I didn't receive good feedback from my student as to how easy it is to interact with Wannier.
Post processing actually very hard until you endorse like a tools.
Yeah.
Yeah. You see, like here, we don't have to go through iterations, right?
Right.
It's an eigenvalue problem. You get the answer.
So yeah,
But that's slightly misleading though, because you don't know a priori where the center is. So you have to do the calculation many times and drop a few minima.
you have to scan the unit cell.
So like
Yeah.
that's your flavor of iteration, is that you have to find the minimum.
But they're not,
Well, not really. Let me make a comment regarding that. If you know the symmetry of the system, sure, you know that the Wannier centers will be either at the center, at these corners, or the other corners. So you only have to run these 3 things.
But if you had something that was fragile, where you say didn't know where the Wannier centers would be, like then you'd have to potentially scan the cell.
Yeah, actually, it's a difficult. So okay, so let me make another comment. If you have a topological obstruction, like in a Chern insulator or a fractal system of quantum spin Hall, there is no such a thing as a preferred site where the Wannier center sits. Instead, you have this, because of the topological obstruction, right? You can nucleate maximally localized. These are not Wannier states. These are overcomplete states. I'll go into that later, but yeah. Okay, but when it comes to atomic limits, this is an atomic limit insulator. You only need to probe three points, and you. Okay, so here I just want to highlight that we can generalize this to 3D. This is a unit cell of a system that has this symmetry. And this is interesting because if you actually look at the Hamiltonian for this system, so this you can play with one parameter in the Hamiltonian, and you can transition between 2 atomic insulators. But if you look at the high symmetry points, which is another standard way of knowing where the Wannier centers would be, the erets of the high symmetry points in both phases are the same. So this is a problem in which the so-called topological quantum chemistry framework is completely useless. It cannot tell apart the 2 phases, but the localizer does. Okay, so now I want to see whether this localizer can do something better than just plot Wannier centers. And I want to exploit the chiral symmetry in the construction of the localizer, because of the we only use 4 out of the 5 gamma matrices. This has the symmetry by construction. And so that means that in some bases, I can always write it like this. And this thing here has a winding number. Okay? And so the interpretation is that when I hit a Wannier center, I can think of this as a topological charge. There's a winding number around this. This is an integer. And it's sort of like count the number of electrons. And it's not restricted to going around one point. I could choose any time. And so with that in mind, we can build a bulk-defect correspondence, right? So what I have here is a 2D system with discriminations of topological defect, where I essentially remove one section of the material and repaste this. Now this thing has a curvature. And typically these curvatures here capture some topological features like a fractional charge. And it's not very well understood how to relate the bulk configuration of the electrons to what happens at the topological defect. But with the localizer, we can sort of like clearly see where the electrons are sitting, right? And so here again we have the same Hamiltonian in 2 different topological phases, symmetry protected topological phases. This is a trivial configuration where the electrons are sitting on top of the ions. And in that case, if I do this sort of like winding number calculation using the localizer, I'll get an integer because I'm enclosing 1, 2, 3 electrons. But in this configuration, if we do something similar to that, I'll have that I'm cutting through an odd number of them. And so if I interpret, going through one of them as one electron, if I cut through them, and think of having half of an electron inside this region, then I have some fractional overall number of electrons modulo E. And so, for example, if you do the same path here, you'll see that you have 1, 2, 3, 4, 5, 6, 7, 9, 8, 7, 8, 9. And so E over 2, right? Which modulo E gives you E over 2. And if you do a density of states calculation, correspondingly find the fractional charge.
Slightly more. Do you really, do you really have these line of Dirac points there?
Yeah.
So that function, I mean, it's really a zero that appears.
Yes.
Because that's not a priori, it's not clear that you have those. That they are really true
In
zeros.
the thermodynamic limit goes
But this is only when you don't have an obstruction, right?
when we don't have an obstruction. Actually, in the thermodynamic limit, even when you have an obstruction, that goes. We'll see the Chern number case. The indicator function flattens. It's not a Dirac cone anymore. But for atomic insulators, you have these points. You could also have in the quadrupole topological insulator something with a quadrupole. For example, you can have 0 points with charge 2, which signals that there are 2 electrons sitting there, and which checks out with the way we're filling the band. And so you can have 2D reps of the symmetry.
I don't know
As you can
why.
Oh, yes. You need certain conditions. So if you have a 2D rep of a given symmetry, then I could see why that has to be the case. So symmetry inverse 2D reps. Okay, so I don't know how I'm doing with time. Okay, yeah. I will now look at the eigenstates of this system. So if I have the localizer here, I want to diagonalize the localizer. We established already that these eigenvalues here are the Wannier centers, and correspondingly, these localizer eigenstates should encode the Wannier functions, right? Now, the problem is that these things here actually have some physical component, but they also live in this embedding space. So how do we disentangle these two at this degrees of freedom? Well, we perform this Schmidt decomposition to separate the spatial degrees of freedom from the embedding degrees of freedom. And so we're going to take, if we order them, in terms of decreasing singular values, we take the one with the largest singular value as the localized state. Okay, so that's how we go from the abstract localized eigenstate to the physical Wannier function. I don't want to call it Wannier function, but localized. Okay, so we show in the paper that the spread at these under open boundary conditions, by the way, so there's simpler versions of these localizers that can be built under open boundary conditions. And so the proof here is for open boundary. We show that the spread of this this localized state is bound by these two expressions here, where this is just a Heisenberg-Robertson uncertainty relation. And then we have this other quantity here that depends on the localizer indicator function. So typically this was 0 when you hit a Wannier center. This is the relative displacement of the center of the function relative to where I put my parameter of the parameter I'm scanning. So this would go to 0, even exactly at the Wannier center. And then this depends on whether I have some entanglement essentially between the embedding and the physical degrees. And so what we see is that in atomic insulators, regardless of whether X and Y commute or not, we always have that this indicator function hits 0 at the Wannier centers, and that the Wannier, this is just a statement that the Wannier function is centered at the Wannier center when my scanning parameter coincides with the Wannier center, and that the singular value is 1, and all the other ones are 0, which means that the physical degrees of freedom and the embedding degrees of freedom are actually disentangled from 1. And so if they commute, then that means that my localized states are maximally localized because this goes to 0. And so this is squeezed. It cannot be farther the spread minimum. And the set of states, 1 unit cell apart, they form an orthogonal basis for my space of occupied lands. So these are the maximally localized Wannier functions. In this case, it's sort of like a
X tilde and Y tilde were these
projected.
These projected cosines.
In this case, it's open boundary conditions. So it's just the projected position.
But then, okay, then you can put a small parameter in front of them in this case.
Yeah, so it's
for kappa.
Yeah, so it's
yes.
Kappa, like, there's no reason that Kappa will give you a preferential treatment.
Okay. Yeah, well, yeah. But I mean, how do you make this small? This commutator.
There's no tuning parameter.
Yeah. So this is just pure hypothetical. What you
Well,
said.
no,
No.
it's for, but there's no topological.
yeah, there's no topological obstructions here. This is for atomic insulation.
Sorry.
So this, but even if you don't have a topological obstruction, you may still have this not commuting. Right? And so, yeah, the interesting finding for me was that even when this doesn't commute, you still have this construct. So the only difference is when they commute, you get it right away. You get maximally localized Wannier functions. If they don't commute, your states are not orthogonal. But then you can do logging orthogonalization if you're really after the so if you just want Wannier centers, you don't have to go to any. Okay, so now the question is what happens if you have a topological obstruction? So the statement is that when you have topological obstruction, no localized Wannier states exist. By localized, I mean exponentially localized Wannier states, and that's given by this invariant. And so what happens is if you take your favorite Chern insulator model and you drive it to a trivial phase where you don't have a Chern number, this is the unit cell. You scan it and you see that you have some Wannier center. Right? This is a cut through the indicator function. And here you have your Dirac cone. But then you transition into the topological phase. And then out of a sudden, this whole thing flattens. So a cut of the Wannier indicator function now like that. Yeah. So crucially, it flattens, but it doesn't flatten up. Instead they all kind of like go to 0. And so this is compatible with the notion that the system doesn't. This looks like a Landau level problem. Doesn't care where the lattice is, essentially. And if you, this is also telling me, if we go back to the expressions for the spread of these functions, that it won't matter much in terms of how tightly localized this state will be. Anywhere in the unit cell, I can get something that's centered around that position. If I will, so this is also an interesting finding. If I pull a Wannier state from, say, this point, it will still give me a function that's localized here. So in that sense, the localizer is very robust. I don't think. Yeah, I can pretty much, I don't need to exactly hit this point to find the maximal localized Wannier function. You will still get it if I go away from it. But if I do the same thing here, then I'll have something that's centered around wherever I put it from.
So your point earlier was that as you go to the thermodynamic limit, these blue bands in the right of the center go.
Yeah.
So one of them will hit 0 even if they don't all.
Mm-hmm. Exactly that. Yeah. Okay, and so the question we have now is, what is the localizer giving us when we have a Chern split? Turns out, we do not get something that's we have something that's exponentially localized. So this is the sort of like the amplitude of the state as a function of distance from its center, or the localizer eigenstate. So that's this thing. So that was surprising because we said, okay, it seems to be incompatible with the notion that we cannot have something exponentially localized, yet we are getting something.
You can't have a complete orthogonal basis. Right?
Exactly. Exactly. We don't have a complete basis in that case. And so one way to think about this is, I told my student, okay, how does this look if we project it into the block basis, right? And so if you take this collection of these localized states, project it into the block basis, and from there you can construct a Wannier, a very connection and a very curvature. What we find is this match. That's Chern. Right? And so we know that there has to be some non-smoothness in my very connection because of the Chern number. Right? Chern number is a statement that I cannot have smooth gauge. So that has to manifest in the very connection with something that makes these arrows, this field here, non-smooth. It turns out there is a ill-defined point at the center of that vortex. So there's recent papers that show that if you want something maximally localized with a Chern band, the gauge that you choose is the so-called vortex gauge, which is exactly what we chose. Okay, but so essentially the localizer is finding the vortex gauge. The difference is that I don't even have to look at the brilliance to find it. I exactly get it from the localizer. If I didn't have the localizer, I would have to construct the gauge with the so-called vortex gauge to then have something maximal. If we restore support over this point here that's ill-defined, then we right away get something that's algebraically because that's 1/r². This is now a Wannier state. So we can use the localizer to also construct Wannier states we're interested in them. But now I'm very interested in the fact that these states here are the overcomplete states, are so-called coherent states that we also see in the Landau level problem. That's it.